being here. I also want to thank the organizers. This conference is very good, and I hope we have it many more times. I'm Marina. I'm part of the Quantum Foundations group of Perimeter Institute. And right now I'm the only thing between you and the dinner at Camarões. Before I start my talk, I want to do some advertisement. So my friend Ila Ying and we wrote, how do I do this? Yeah, we wrote a kid's book about Bell's theorem. And I had some copies in the beginning of the week, but they're finished. But if you want, you can talk to me, and then I can send you the PDF and you can print it. If not, this is going to be on Perimeter Institute's website at some point this month. Okay, so today I'm going to talk about this paper that we put together, all of these people and I. In December, we put it on archive. And this is a resource theory project. So what are the kinds of objects that I'm going to be interested in this resource theory? The first kind of object is something like this. So it's a function from a variable x to a variable y. Just a disclaimer. So we are at Quantum at the Dunes, but I'm cheating a little bit because everything in this paper is classical. But in the end, if I have time, which probably I won't have, I can tell you that recently, Rob and I have been thinking of ways of generalizing this project to the quantum case. But right now, what we have in this paper is in the classical case. Okay, so since it's in the classical case, I just have a random variable x and a random variable y and a function between them. And I want to quantify causal influence in this object. There's also a different object that I'm going to be interested in, that I'm going to represent like this. This is a probability distribution over the possible functions from x to y. And this appears when I don't know what is exactly the function from x to y, so I have some uncertainty there. Later I'm going to give examples to you, so this is going to be more concrete. Okay, so right now I'm going to tell you a story that kind of motivates this resource theory and kind of shows a cooked up situation in which this could be useful. So imagine that I have a communication channel between Alice and Bob, just a classical communication channel. So Alice has the variable x, and then she inputs it into the green communication channel. But this channel can be noisy and apply some function to the variable x, and then output a different variable y to Bob. I'm going to assume that x and y are binary, so they have only two possibilities. This means that the function that the green channel applies could be identity, so nothing changes, flip, that is y is just the flip of x, or it could be reset to 0, reset to 1. That's the situation in which y completely ignores what is x and just outputs always 0 or always 1. Okay, here, more than just the communication channel, I'm going to assume that this channel also leaks some information to the environment about what is the function f that was applied. This information I'm going to call a flag variable. It's just a variable that flags like what was the function that was applied. And this is in the environment. Bob can measure it or not. So let's look at a few possibilities of whether Bob obtained information about this flag variable or not. So the first possibility is when Bob has no knowledge about the flag variable. So it's just the usual type of communication channel that people study. In this case, the best characterization that Bob can make of this green channel is a conditional probability distribution P of y given x. Of course, to obtain this characterization, they need to do some rounds of communication, and then Alice needs to tell Bob via perfect channel what it was the value of x in those rounds. But the important thing is that they make this characterization to later see if they can use the green channel to communicate or not. So here's an example of a conditional probability distribution. It's the case where regardless of whether x is 0 or x is 1, the probability over y is uniformly distributed. So here, this notation of the square brackets, I'm going to use it throughout the whole talk. And this means that the thing that's inside the brackets is the potential value that this variable takes, and this is the probability. So here it just says that y has half chance of being 0 and half chance of being 1. Okay, so in this case, where Bob does not have any knowledge about the flag variable, the relevant resource theory is Shannon theory. So it's just normal theory of capacity of classical channels. And then in this paper, this was formalized as a formal resource theory in modern terms. And I'm not going to talk about it because this is very well studied. So let me look at the other extremal case regarding how much information Bob has about the flag variable. The case where Bob completely learns the flag variable. So there's the ruler there because he went to the environment and obtained exactly what is the function that this green channel applied. In this case, the best characterization he has is obviously just the function f. And since I'm in the binary case, remember I have 4 possibilities for this function. And these 4 possibilities, they can be divided into 2 classes. The first one is identity and flip. Those are functions that transmit causal influence. Because with them, Bob can look at y and then learn what is x. But reset to 0, reset to 1, they're useless for communication in this case. So they're functions that do not transmit causal influence. Because when this is the function, y just has no functional dependence on x. Okay. The relevant resource theory for this case is what we call the resource theory of causal influence. That is the first one that I'm going to show to you. So I'm actually going to show you 2 resource theories. The second one appears when we have an intermediary situation where Bob only obtained partial knowledge about the flag variable. So I have a broken ruler there. In this case, the best characterization of the channel that he can have is something called a probability distribution over functions. Let me give you an example. So 2 examples, actually. In the first example, Bob knows that there's half chance of being identity and half chance of being flip. But in a specific round, he doesn't know if the channel implemented identity or flip. But he knows it was half chance of identity, half chance of flip. In the second example, there's half chance of reset to 0 and half chance of reset to 1. Now, I can ask you, what is the conditional probability distribution, P of y given x, that comes from each of those probability distributions over functions? For this case, it's easy. It's just half chance of y being 0 and half chance of y being 1, always. But as it turns out, for this case, this is also true. Because when you send, for example, x equals 0, you're going to have half chance of y being 0, half chance of y being 1. And in the opposite, you're going to have half chance of y being 1, half chance of y being 0. So those 2 probability distributions over functions, they give rise to the same conditional distribution P of y given x. Therefore, the probability distribution over function is more informative than just a conditional distribution. And here I want to argue that the correct object on which to ask if you have causal influence or not is this object, the probability distribution over functions. And why is that? This is because if you only have this, this object, this could be compatible with those 2 possibilities. But this first one, you definitely have causal influence in that channel. You just don't know if it's via identity or flip. So this is just a problem about your knowledge. But the channel has causal influence. In this case, you know that the channel does not have causal influence, right? Okay, so with this, later I'm going to, just one thing I forgot to say in the beginning. Later I'm going to connect back these resource theories that I have with quantifiers of causal influence that people usually talk about in literature, like, for example, the average causal effect, if someone heard about it. But this point here is going to be important there. Okay, so here I say that this is more informative, but even more than that, it is also, I want to argue that it is more useful for this communication task that I cooked up here. So in this first case, so if Bob knows that the probability distribution over function is this one, and suppose that Bob has the possibility of extracting more information from the environment to learn the flag variable, okay? But it's expensive, so he wants to know if he should do that or not. In the first case, the answer is yes, you should do that. Because if you extract more information, you learn that exactly it was identity or exactly it was flip, then you can use this channel to communicate. But in the second case, Bob knows that he shouldn't even bother to get more information about this flag variable because it's going to be useless either way. It's just there's no causal influence. Okay. So in this case, the resource theory that is relevant is the second one I'm going to present to you, the resource theory of knowledge of causal influence. And then here's a summary. So in the case of Shannon theory, the object of interest is the conditional probability distribution P of y given x. For the resource theory of causal influence is the function, and for RT of knowledge of causal influence is the probability distribution over functions. Okay, now let's go to them. I'm going to first tell you about the resource theory of causal influence. As I said, the object of interest is this function. What is a generic transformation in this function? The most generic transformation you can have that take deterministic functions to deterministic functions is something like this. Like this? Yes. Where you have some pre-processing, and then you have a side channel that feeds into some post-processing. And then this is going to give me a second function. However, you can see that this transformation here can transform something that has no causal influence. So for example, if f is reset to 0, here I can just go through the side channel and obtain an identity. So this type of generic transformation can create causal influence. But here I'm trying to construct a resource theory. For resource theories, our goal is to find what are the operations that do not increase my resource. And here my resource is causal influence. So I want operations that do not increase causal influence. As it turns out, the set of transformations that's like the most generic set of transformations that do not increase causal influence here is when you remove this side channel, and then you just have pre and post processes. In this case, we call those the free operations, the free transformations, because they're the ones that do not increase my resource. Okay, and with these free transformations, you can, for example, transform flip into reset to 0. Very simple, we just post-process with reset to 0, so whatever was before just turns into reset to 0. But the other way around is not possible with only pre and post processings. Therefore, we can obtain the total order of this resource theory, which is just this. So you just have identity and flip that are in the same equivalence class that then dominates the equivalence class of reset to 0, reset to 1. Those have no causal influence. Those do have causal influence. Okay, so this resource theory is completely solved for the binary case. And in fact, it's also completely solved in general. So here, it's a case where x and y can have different cardinalities. But what we proved is that f can be transformed, a function f can be transformed into a function g via those free operations, pre and post processing, if and only if the image of f is larger or equal than, the size of the image of f is larger or equal than the size of the image of g. So if you remember, the reset to 0, size of the image is 1. Identity, the size of the image is 2. So, yeah, so this is just a special case of this. Okay, so now let's go to the second resource theory, the resource theory of knowledge of causal influence, where the objects of interest are those probability distributions over functions. Okay, again, what is the most generic transformation I can make on a probability distribution over functions that gives me back another one? Something like this, a pre-processing, a post-processing, but now I can input some ancilla variable that has some probability distribution. Before I didn't have that because those were deterministic functions, but now I can have this. But again, I cannot have those side channels if I want the free transformations because they can create causal influence. So the most general free transformations that I can have are this. So these are the free transformations of my resource theory when I have a pre and post processing and then can be correlated by a common cause. However, since this common cause is not like x prime does not influence the common cause, I'm not creating any extra side channels that introduces causal connection. Okay, so now if these are the free operations, what is the resource theory that we obtain from there? I'm going to just show you one example. So those are the two guys that we saw in the beginning, like in the communication story. And this first one can be converted into the second one in a very simple way. You just post-process with reset to 0 half of the time and with reset to 1 half of the time. So this is a resource conversion that's a bit boring because I only used the post-processing, I didn't use the common cause. There are some where you do need the common cause and I would go through it with you, but I don't have time. But this is just an example. Note that if you have two resources, there are two probability distributions over functions that only have support and reset to 0, reset to 1, they are mutually interconvertible because you can always just post-process with R0 p of the time and with R1 1 minus p of the time. And so this is the class of free resources, meaning of probability distributions over functions that don't have any resource in my theory. They don't have any causal influence. Okay, so, but now I want to tell you more things about this resource theory. I want to tell you about what are the monotones of this resource theory. So monotones, they are numbers, like numbers, that such that if one resource can be transformed into another, then this monotone for the first one has to be larger or equal than the monotone for the second one. And if you have a complete set of monotones, that means you characterized your whole resource theory. You can look at a guy and say, by this list of numbers, this list of monotones, I know exactly where in the spatial order this resource lives. And as it turns out, we did find the complete set of monotones for this resource theory in the binary case. I'm going to explain that. I'll first tell you about this parametrization of a probability distribution over functions. This is just a parametrization. So you have a probability distribution over 4 possible values. So this means you have 3 parameters. And they look ugly, but they're actually very easy. So beta is the parameter that goes in front of the term with identity and flip. And then 1 minus beta, the rest. So this means that beta is the weight on the sector that carries causal influence, because only these guys carry causal influence. Those guys don't. Okay, now if you know you are in the sector that carries causal influence, alpha kind of measures how polarized you are towards identity or towards flip, or if you're kind of in the middle. And gamma is the same thing, but for the sector without causal influence. So it's just a parametrization. Now with this parametrization, this is the complete set of monotones for this resource theory, just 3. And now I'm going to interpret each one of them and show you what do they quantify. So this first one is beta. Remember, it was the weight on the sector that carries causal influence. So beta is the probability of causal connection. An example of 2 guys that have a different value of beta is the same guys that we were always seeing. So they can be differentiated in this resource theory by this monotone beta. So this beta is kind of like the strength of the causal influence, or like how sure you are that you have causal influence. The second guy, which is the absolute value of alpha, it measures how much knowledge you have about the precise nature of the causal connection when you know you have causal connection. So remember, it was the weight between identity and flip. Here's an example. So these 2 guys, both of them have complete causal influence, right? There. In both of them, you are sure that you have causal connection. But still, the first one is more resourceful in our resource theory than the second one, because in the first one, you're sure of what is the precise nature of this causal connection. The second one, you don't know. The third monotone is a bit harder to explain. I'll do my best. But it's okay if you don't understand this part. I have another interpretation of this monotone later on. So this third one has 2 interpretations. This third monotone, it is how much causal connection has to be sacrificed to increase the knowledge of between R0 and R1. So let me explain it to you through an example. So I have those 2 guys. Note that they have the same value of beta, 1/3, and they have the same value of alpha, like inside the sector with causal influence, you have complete certainty that it is flip. But still, this one is more resourceful than this one. And that's because if you remember that I had reset to 0 and reset to, if I had probability distributions over functions that had support only on reset to 0, reset to 1, they can always be interconverted to one another. But here, I have some support here. If I want to increase the knowledge that it's reset to 0, I would need to post-process with some reset to 0. So here, between those 2 guys, I'm unsure if it's reset to 0 or reset to 1. If I post-process with some reset to 0, I would be sacrificing some of the causal influence to get something that's more sure here. So this third resource is kind of how much causal influence you have to sacrifice to increase your certainty that it's either reset to 0 or reset to 1. So then in this resource theory, we kind of have 1 monotone that quantifies how sure you are that you have causal influence. Second monotone that tells you what is the precise nature, like how much knowledge you have about the precise nature of the causal influence. And the third one, that's kind of trade-off between causal influence and knowledge of the reset to 0, reset to 1. So this is why we call it the resource theory of knowledge of causal influence. Now let me give you another interpretation of those monotones back in that communication story that I told you. So the beta, we already saw the interpretation of that. It was kind of like, if I look at this example, for this one is useful to learn more about F, for this one is useless. So I kind of see that in this story, this guy is more valuable than this guy. And indeed, in our research theory, this guy is more resourceful than this guy. The second monotone, this guy is more valuable than this one, because here you can learn a lot, like Bob can learn a lot about X without learning anything else about the flag variable. But here, he cannot. So, yeah, this guy is more valuable than this one, even though both of them have complete causal influence. And for the third monotone, here's the alternative interpretation that I told you before. If I look at those two examples, that they are differentiated only by the third monotone, first and second is the same. Note that for the first one, if Bob post-selects on the value of y being equals to 1, he's completely sure that this channel in this round, like if I see y equals to 1, I know that in this round there was causal influence, because I only have reset to 0 here. So if I post-select on y being equals to 1, I know that in this round that came from this. However, here, it doesn't matter, like if I post-select on 1 or 0, he's still not sure if it came from the sector without causal influence or the sector with causal influence. So this is also a reason why you would think that this is more valuable than this. Okay, cool. Now the last thing I want to say is, what about other ways of quantifying causal influence that were previously there in literature? And in particular, I want to talk about the average causal effect. So actually, maybe this is a change of topic. So before that, is there any question to here? Okay. So I'm going to talk about something that's called the average causal effect, that in causal inference literature, people use this a lot. So here, I'm only in the case where I have x pointing to y, and I don't have any common causes between x and y. I don't have any confounders. In this special case where you don't have any confounders, the average causal effect is just the probability that y equals 1 when x equals 1, minus the probability that y equals 1 when x equals 0. And it's, again, because I have no confounders. So this kind of measures how much the distribution over y changes when you, and also just for the binary case. But it kind of measures how much the distribution over y changes when I change the value of x. And people have been using this as a measure of causal influence. But I want to argue that this cannot be a measure of causal influence per se, because it is based on the conditional distribution, P of y given x. Or in the case with confounders, it's something called a do conditional. And as I argued before, this object, it doesn't make much sense to ask how much causal influence you have just by looking at this object, because it can come from a situation with no causal influence, but it can come from a situation with complete causal influence. And the average causal effect for this is 0, so even if it came from this. But the average causal effect can be recovered from our resource theory in the following way. So we proved that, again, in this causal structure, if you have, okay, let me explain this. So if you have one conditional probability distribution P of y given x, and then you look at the list of all of the probability distribution over functions that give rise to that same conditional distribution. So in that case, I had 2 giving rise to 1, but look at the list of all of them. Now look at the value of beta, so the probability of causation for all of those guys. Pick the one that has the smallest value of beta. This value is going to be the absolute value of the average causal effect. So in this example here, the average causal effect, the value is 0. And indeed, for this guy, the guy that has the minimum beta is this, when beta is 0. So in a sense, the average causal effect measures the minimal amount of causal influence that is sufficient to obtain that P of y given x, but not necessarily the amount of causal influence that actually happened in that situation. Okay. And also the average causal effect, I'm not, it is kind of a coarse-grained monotone of our resource theory too. Like, it does not measure causal influence per se, but it's kind of a coarse-grained monotone in this resource theory. So, yeah, that's it. Thank you.
Okay, we have time for some questions.
Thanks for the talk. So there was something that came to my mind, like in a way, it resembles some of the things you explained. Look to me like when you have a mixed state, you have an ensemble, and there are different ways of making a mixed state. And for instance, I could also think like, okay, if you give me the identity, it can be the convex combination of product states of Bell states, and then if I know, I could argue that the ensemble with entanglement hasn't that in the same way as you were mixing, things with causal. I don't know.
Yeah. So actually, maybe then I can say a little bit of what we were thinking when we want to make the generalization of this to the quantum case. So here, since we're talking about functions from x to y, we were thinking actually about channels, right? From one quantum system to another one, and not about just states, but about channels. However, the channels, like the quantum channels, they are not the analog of this object. So, yeah, quantum channels are not the analog of this object. They are the analog of this object, because you can have something like this with quantum channels, like that you have a mixture, and yeah. So the problem on doing this generalization is then, what is the analog of this object? If you think that the analog of the functions, of the pure functions, deterministic functions, is just a unitary, for example, the analog of the probability distribution over functions cannot be just a probability distribution over unitaries, because not every channel can be recovered in this way. Like, I have channels that are not mixed unitaries. So then, yeah, we don't know like what is like a quantum probability distribution over unitaries, a quantum state over unitary. We don't know. Yeah, I don't know if I answered as well.
Okay, my question was not about the quantum generalization. Okay, maybe for the quantum generalization, you have to use extremal channels, it seems, no? Like for the left part, because you are saying that not all channels are probabilistic combination of unitaries, right? Mm-hmm. But all channels are probabilistic combination of extremal channels, obviously. I was simply the fact that you have using here things like, okay, there are different realizations for the right-hand side, and then you say, oh, some realizations are different. And when I know more about the realization, I can see this difference. Mm-hmm. This is something that could apply to other contexts as well. This was my comment.
Final question. Still some seconds. I guess everybody is hungry, eh? Okay, thanks, the speaker again.
There you go.